Welcome to part 4 of the Conservation Innovation Grant Insights webinar series. The purpose of these webinars is to share insights into the nutrient-led third-party technology evaluations that were conducted under our 2020 NRCS Conservation Innovation Grant Award. I'm Corinne Brown, Analyst of Sustainability Research and Initiatives here at Nutrient. And in today's webinar, we'll be exploring the various technologies that can make up an integrated manure management system on commercial dairy farms. First, let's go over our objectives for this webinar. After listening to today's webinar, you should be able to identify the meaning of an integrated manure management system, understand the purpose of solid-liquid separation as the foundation for downstream manure management technologies, and compare the functionality of mechanical, polymer-assisted, and membrane-based separation approaches. Additionally, the webinar will allow you to review some of the pre- and post-separation technology practices used on dairies, summarize the environmental and economic benefits of integrated manure management systems, and recall the goals of nutrient CIG evaluations and resources available for further interest to see how integrated manure management systems fit into the project. Now for a bit about Nutrient. Nutrient was founded in 2015 to help farms identify ways to reduce their environmental footprint while making it economically viable for them to do so. Our forward-thinking members include milk cooperatives and dairy organizations representing nearly all U.S. dairy farmers. In 2020, Nutrient received nearly $700,000 from the NRCS to evaluate 15 technology systems and practices with the addition of one literature review, aiming to demonstrate how these systems reduce the environmental impact of dairy manure with a focus on water quality. Our goal is to improve access to EQIP funding for innovative technologies under Conservation Practice Standard 629 and other associated standards. Garnering universities nationwide, we collect samples, document the results, and produce comprehensive reports. These reports will be shared with the NRCS and the dairy industry to encourage the adoption of sustainable dairy practices. With that, I'm excited to introduce Jeff Porter, Technical Advisor here at Nutrient, an agriculture engineer with extensive background with the NRCS, where he served as the leader of the National Animal Manure and Nutrient Management Team.
Thank you, Corinne. Greetings, everyone. It's good to be with you today. Now, even though this Conservation Innovation Grant looked at a number of different manure management technologies, there were a couple of items that stood out. First, more than one technology may be needed to reach the goals and the objectives for this particular dairy operation. See, there is no silver bullet to address resource concerns. Second, for most of the technologies evaluated, waste separation played an integral part. And during this webinar, I'll be talking about several of the technologies we evaluated through this CIG with a special emphasis on waste separation. And even though many of these practices or unit processes, which is what I like to call them, operate separately, they often function together with other unit processes to create a functioning integrated manure management system. Now, the easiest way to look at this is to determine what comes into the system or operation and then what goes out, looking at the big picture, you might say. Unfortunately, this may not be the most effective way of evaluating manure management technologies. One may not know what goes on inside the operation to get to the individual unit process values. Even though there is an overall system or grouping of technologies, each process in and of itself should be evaluated separately to determine how it is affecting the operation of the overall system. And it's important to break the manure management system into its individual unit processes. In this overhead view, we see manure transfer and storage, which really do not provide adequate information on evaluating this system. So we need to dig deeper into the system and the component operations. This is where it is important to understand the difference between systems and individual or unit processes. These processes make up the overall system. And as one looks at the treatment of animal manure, the individual operations can normally be divided into three main groups of processes. You have physical processes, chemical processes, and biological processes. And when looking at waste separation, most of the processes are physical. But there are some technologies that utilize chemical processes to enhance the overall separation process. When looking at a dairy and the overall system operation, there are a number of factors that should be evaluated to help the producer select the technology or the technologies that will best meet the needs for that particular dairy. And here we just see a few of the items that should probably be addressed. And I think first and foremost is that of the landowner's goals and objectives. What do they hope to get out of implementing any of these technologies or practices that they are currently looking at? Are they actually addressing any resource concerns that they may have? Are they dealing with any excess nutrients? Do they have more nitrogen than they need, or more phosphorus than they need, or do they need to separate it into different partitioning of those nutrients because of the nutrient imbalance of how much the nutrient levels are in the manure versus what is needed for the crop production? How much land is available for them to land apply the manures? And also how much land is required based on how much manure they do have. How do they want to handle the waste streams? Do they want to look at just dealing with solids? Do they want just liquids? Or do they want to look at a combination of both? These are just a few of the things that they need to be looking at when trying to determine what technology is going to be working best or will work best for their particular system or operation. Now, as part of this conservation innovation grant, we looked at a number of different technologies and processes, and all of them were centered to a certain extent around waste separation. And I've broken our technology reviews into three sections: pre-separation, waste separation, and post-separation. Even though there are many more technologies and more are being added almost on a daily basis, these are the ones we reviewed during this study. Now, one will notice that I included vibratory screen under both pre-separation and separation. As we have reviewed various technologies, we have seen vibratory screens used for both purposes. Now, to review the information for each of these technologies, these evaluations that we did, we're going to be addressing that towards the end of this webinar. Here we see an example manure management system. Since the dairy uses sand bedding, sand separation is necessary for a few reasons. First, the sand can be reused for bedding, which helps to reduce the cost of purchasing additional bedding. Second, sand is very gritty and can have negative impacts on mechanical equipment downstream. Sand removal will help extend the life of other waste separation technologies. And once the sand has been removed, the waste stream flows through a coarse solid separation system. Some common technologies include screw presses, rotary drums, and slope screens. Now, even though most phosphorus and organic nitrogen is retained in the manure solids, only a small portion, around 10 to 15%, are captured in the coarse solids. And if higher percentages of nutrient removal is needed, fine solid separation technology such as centrifuges can be utilized. Approximately 50% of phosphorus and organic nitrogen can be collected in the fine solids. Utilizing ultrafiltration or polymer assist separation can capture nearly all of the suspended solids, including nearly all of the phosphorus from the waste stream. Reverse osmosis can also be incorporated to remove nearly all of the dissolved solids and the remaining nitrogen. Now, ultrafiltration and reverse osmosis result in multiple liquid streams with varying nutrient loads, whereas the polymer assisted system, you can have both liquid and solid as your waste streams. The level of waste separation that is needed is dependent on the end use and, again, the producer's goals and objectives. Land application of liquid manures can be utilized following many of these separation technologies. Let's go into a little more detail into the importance of waste separation and the factors to consider when looking to handle manure and the end uses. When dealing with manure management, there are usually a number of different challenges or resource concerns that may need to be addressed. Even though every dairy operation is unique, similar challenges are often encountered. Both water and air quality issues are common concerns. Due to manure solids, waste transfer through pipes, and irrigation nozzles can be challenging. Manure nutrient and crop requirement imbalances often have to be addressed as well. Now, all of these concerns and other issues are why solid liquid separation should be considered when dealing with manure management. Nutrient partitioning is a common reason for implementing waste separation. Removal of solids from the liquid waste stream minimize solid buildup in storage facilities and can also lower energy costs by reducing agitation and pumping costs. Other treatment unit processes, such as composting and biochar production, benefit from waste separation practices. Here we see a number of the technologies evaluated through this Conservation Innovation Grant, all relying on solid liquid separation as part of the manure management system. The following slides provide a more detailed description of these technologies and their roles with solid liquid separation. The McClanahan mechanical sand separation system removes sand from the waste stream to be reused as bedding and served as a pre-separation technology, removing grit, reducing wear and tear on downstream equipment. It also reduces the buildup of sand, which is hard to remove from waste storage facilities. There are several models and configurations available for varying herd sizes and layouts. Screw presses and slope screens were used in most of the evaluations to prepare the waste streams to improve downstream technology functions through our Conservation Innovation Grant reviews. Rotary drums and vibratory screens are also popular coarse solid separation technologies. These solids, for the most part, are stackable. Depending on the results, moisture content, and different things, these solids could be used for bedding, composted, or directly land applied. Removal of the coarse solids help to reduce the solids loading and operation and maintenance of downstream fine solid separation unit processes. Coarse solid separation technologies can be adapted for a range of dairy operations from small to very large. A centrifuge centrifuge was evaluated on one dairy and served as a part of the separation system prior to membrane technology on another operation. This technology operates at very high speeds, generating around 3,000 G-forces. The centrifuge removes smaller particle sizes than coarse solid separation, and as a result, a higher percentage of phosphorus and organic nitrogen is removed from the liquid waste stream. Centrifuges are generally used on larger dairy operations. Coarse solid separation is normally the first step for most manure treatment systems. Even though sand separation is a waste separation technology, for this presentation, I've categorized it as a pre-separation unit process. There are numerous technologies that could be used to accomplish sand separation, both mechanical and passive. Coarse solid separation removes the largest particles from the waste stream. This material can be used for bedding, compost, direct land application, or other uses. Fine solid separation helps to remove more of the suspended solids along with a higher percentage of the phosphorus and the organic nitrogen from the liquid waste stream. Now, as seen in the image on the far right, coarse and fine solid separation are compared. The material on the left side of the image show that the particle sizes are smaller, and the darker color indicates that more nutrients are retained with fine separation when compared to coarse solid separation technologies. Once the initial coarse and fine separation has been completed, other unit processes can be implemented. Now, let's just take a look at membrane and polymer-assisted systems that Nutrient evaluated through this Conservation Innovation Grant. Some dairies need to remove additional nutrients or better partition the nutrients so that they can utilize them more effectively. Aqua Innovation's membrane-based ultrafiltration and reverse osmosis system was evaluated through this CIG. Coarse solid separation is a critical component of the overall functioning of this system. Removal of the coarse material helps the membrane filters operate more effectively and reduces operation and maintenance while minimizing the amount of backflushing of the membranes. This system generates multiple liquid waste streams. The UF concentrate contains nearly all of the remaining phosphorus, while the filtrate still holds a large portion of the potassium and inorganic nitrogen. Even though the ultrafiltration system can run independently, some operations may also choose to add reverse osmosis to concentrate the remaining nitrogen and potassium in the RO concentrate, leaving water that may meet discharge quality. The clean water is around 30% of the original manure volume. Another option for removing additional nutrients from the waste stream is by adding polymers such as with the livestock water recycling or LWR system. Again, coarse solid separation is an essential part of this technology. The more solids removed prior to entering the system, the less polymer is needed to effectively remove the remaining suspended solids along with the phosphorus and organic nitrogen. One of the differences between membrane and polymer systems is that the polymer enhanced separation generates a solid product, which we discussed just a little bit earlier. Since these solids tend to have high moisture content, another separation technology, such as a screw press, could be used to dewater the solids so that they can be stacked and more easily be moved. Now, it should be noted that this additional separation process can allow a portion of the phosphorus to re-enter the liquid stream. Processes up to this point make up what's called the first wave system by LWR. If additional processing is desired, a reverse osmosis unit can also be added, generating a high inorganic nitrogen concentrate and water which may meet discharge requirements. Systems can be developed for small, around 100 cows, to large dairy operations. Here we see the primary components and operation of the two nutrient recovery systems that were evaluated by Nutrient. As can be seen, both technologies require some level of solid liquid separation prior to implementation of the unit processes. Both perform nutrient partitioning, and if needed, a portion of the waste stream can be treated to clean water with reverse osmosis. There are many uses and applications for the solids and liquids from a manure waste stream. The vast majority of the material is land applied and utilized as a nutrient and carbon source. Let's take a look at some of the different applications for waste streams. One of the unit processes that Nutrient evaluated was the 360 rain adaptive irrigation system. This system can apply fresh water, fertigation, and liquid manure, as well as a combination of any of these. Manure solids up to 10% have been land applied effectively with this technology. Because of the global positioning system utilized with this unit, numerous nutrient applications can be made accurately on a variety of field configurations. The drop nozzles allow for manure, nutrients, and water to be applied near the root zone, maximizing nutrient uptake while reducing volatilization and odor issues. One unit can irrigate up to 200 acres. As mentioned before, the amount of solids removed from the manure can impact how the various waste streams are going to be utilized or what byproducts could potentially be produced. The coarse solids can be used in a number of ways. At the right moisture content, the solids can be used as bedding or as a main component in generating compost. There are also efforts in generating biochar as a stable high carbon product. Besides land application, other markets are being developed for biochar. These coarse solids can also be land applied. As more solids are removed from the waste stream, nutrient partitioning becomes an important result. As phosphorus and nitrogen are partitioned, field applications of these products can be more designed to meet crop needs, reducing the reliance on commercial fertilizers. Dealing with manure management is something that all dairy operations have to address. Even though most animal manure is land applied for crop production, there are other applications and byproducts that can be generated from this valuable resource. For most of these applications, processing of the manure normally begins with solid liquid separation. Depending on the goals and the objectives of the dairy operation, the unit processes implemented provide opportunities for more usable nutrients and other byproducts. Practices to generate fine solid, membrane-based separation, polymer-enhanced separation can be utilized following coarse solid separation processes. Implementation of these and other practices provide opportunities to potentially generate additional income, reduce operational cost, or improve land application methods. Throughout this conservation innovation grant, Nutrient has evaluated a number of unit processes, focusing on the impacts on water quality. Even though each evaluation focused on an individual unit process, most of the manure management operations included multiple unit processes to make up an integrated system. I'd like to take just a few minutes to look at these systems, operation maintenance, and estimated capital and operational costs. Here we see a flow diagram of a dairy manure management system located in Wisconsin. For this operation, we evaluated two specific unit processes, mechanical sand separation and polymer enhanced solid separation. This integrated system consisted of several other unit processes. Prior to the mechanical sand separation system, the liquid waste stream flowed through a sand settling lane, allowing the coarser sand grains to settle. Following the mechanical sand separation, it was found that there was less than 3% organic material remaining in the sand, which was going to be reused for bedding. The remaining liquid waste stream flowed over a slope screen with a roller press to remove additional liquid from the removed coarse solids. Liquid was then mixed with a polymer to create flocks and capture most of the remaining phosphorus in the waste stream. This material flowed over an inclined screen, dewatering some of the flocculated liquids. These solids then passed through a screw press to further dewater the solid material. Now, it should be noted that the screw press broke some of the flocks, and the phosphorus level in the resulting liquid stream was a little bit higher than the liquid collected from the inclined screen following polymer addition. The final liquid was transferred to a holding pond. This liquid could be used for flushing the freestall alleys and land applied. Now, even though not evaluated as part of this study, the dairy also has a reverse osmosis unit for generating clean water. Since the polymer enhanced solids had high phosphorus levels, this material could be hauled longer distances at lower cost for land application. For the unit processes evaluated through this conservation innovation grant, there are a number of potential environmental benefits worth discussing. Reducing the solids loading in waste storage facilities can have a small impact on storage volume. Additionally, less solids accumulation in the storage system can impact operational costs by reducing agitation time prior to land application. Nutrient partitioning allows for more efficient land application for crop production, placing nutrients where needed, better matching the crop demand. This helps to reduce runoff and leaching issues. Removal of solids from the waste stream improve land application methods by reducing downtime from clogged nozzles or injection systems. Removing solids from the liquid waste stream also reduces odors during handling and storage. Here we see the estimated capital and operational costs for some of the coarse and fine solid separation technologies. Ancillary components such as piping, reception pits, roofs, and covers can impact these costs. As mentioned before, goals and objectives as well as system performance must be considered when trying to select the best separation technology for the dairy operation. It should be noted that as the amount of solids and as drier solids are desired, capital costs tend to increase. On this slide, we see some of the estimated costs for nutrient recovery separation or nutrient partitioning systems. These fine solid separation technologies are climate sensitive and will require roofs and covers. Other ancillary practices such as piping and reception pits will likely be needed as well. Capital costs for the polymer assist systems are only for the first wave process. If the reverse osmosis component is added, monthly costs will also increase. Operational and maintenance costs should also be considered when looking at selecting a nutrient recovery system. As mentioned earlier, the ultrafiltration system generated different liquid waste streams, while the polymer assisted system generated both liquid, low phosphorus, and solid, high phosphorus waste streams. The adaptive irrigation system allows flexibility for land application. It can generally be used with waste management systems that have, as a minimum, coarse solid separation. Both capital and operational costs should be taken into account when looking at land application technologies. Not only should one consider the environmental benefits of solid liquid separation, but there may also be economic and operational benefits from implementing these practices. Since sand is an inert material, it does not provide any nutrient value and would improve land application if removed by sand separation technologies. Sand removal reduces wear and tear on gears and propellers, increasing longevity. Agitation costs are reduced when sand and solids are removed prior to liquid storage. Removal of sand and solids can also allow for improved automation of land application systems. Less clogging of transfer pipes and nozzles would be expected. Now, since less water is contained in separated manure solids, this material can be transported longer distances more economically. Clean water from the advanced nutrient recovery technologies can reduce the reliance on fresh water and can be utilized for a number of applications on a dairy. Now, with an adaptive irrigation system, nutrients can be placed near the root zone, improving nutrient uptake and potentially reducing the amount of fertilizers required for crop production. When looking at a waste management system, many factors need to be considered. Now, for most of these systems, solid liquid separation is likely one of the first practices to be installed. If sand is also an issue, sand and grit removal can reduce downtime for downstream practices. Coarse solid separation can improve the performance and longevity of other technologies that may be added. As an integrated system is being planned, each technology should be installed so that it will not interfere with the placement or performance of future practices. Now, information on technology selection will be addressed in the next section of this presentation. At this time, I'd like to return control to Corinne.
Thanks, Jeff, for your valuable insights on integrated manure management systems and nutrient SIG evaluations. Let's now walk through some of the various resources Nutrien offers. We have many experts on our team who are happy to spend time with you as a farmer, cooperative, or other industry stakeholder looking to learn about additional on-farm sustainability practices or to hear more about Nutrien. The Nutrien website, www.nutrient.com, houses many resources, one of those being the Nutrient Solutions Catalog. This is an online collection of solutions including manure additives, NRCS practice standards, and hundreds of service and technology providers. Nutrient's Resource Library is a place where audiences can find a compilation of webinars, peer-reviewed articles, white papers, and more. And Nutrient's blog posts host various articles and posts about recent dairy industry happenings, specifically pertaining to dairy sustainability. You can also locate various webinars on the Nutrient LLC YouTube channel, including 3 other videos part of this webinar series on dairy composting, decanter centrifuge, and vibratory separation screen technologies. Nutrient's quarterly newsletter is also a great resource to learn about Nutrient's latest updates and dairy sustainability news. Use the QR code on your screen to subscribe to our newsletter for timely updates and industry news, as well as access Nutrient's contact form to get in touch with us. If you're curious about the other nutrient SIG technology evaluations, Visit Nutrient SIG webpage, where you can view project materials such as vendor snapshots, evaluation summaries, comprehensive reports, webinars, and informative videos. But do note that evaluations and deliverables will be added to the webpage as they're completed, and not all technologies will include all the listed deliverables. I'd like to give a very special thank you to our partners indicated on the slide who collaborated with Nutrient as part of the various evaluations Jeff mentioned throughout the webinar. And a big thank you to you for joining us today.